Welcome. This video continues our review of some C++ concepts. In this video, we're reviewing pointers. Before I can get into what a pointer is, I have to say what an object is. A pointer points at an object. So an object is a value in a program. For example, I could declare string name that creates a object called name, and the data type of name is string. I would say that name is an object. I could also declare int score that creates a object of type int that's called score. An object is stored at a specific location in memory. This is something that is important in C++. It's less front of mind in other programming languages, but in C++ you have to be aware of this and work with the fact that every object is stored at a particular location in computer memory. The way that computer hardware works is you have this RAM memory. A typical computer has billions of bytes of memory called gigabytes. So if I have a 8 gigabyte RAM computer, then there are 8 billion bytes of memory on that computer, and this works like a big array of bytes. So they are indexed starting at 0, working up through 7,999,999,999. Every one of those indices is called an address or a location in memory, and if my program created these two objects, then one of those memory addresses would be where name is stored, and a different address would be where score is stored. This can get kind of complicated with objects at different locations and pointers going between them, and we use sketches to help us visualize what's going on. That's why we're emphasizing sketches in these videos, and we'll be doing sketching all throughout the class. A pointer is a location in memory. So the data type of a pointer can store any location in memory, and that's what a pointer is just a location where an object could be or maybe could not be. So we distinguish between a valid pointer. A valid pointer is a location in memory that does indeed have a valid object, and an invalid pointer, which is not that. So an invalid pointer is a location in memory, but it's not a location where an object exists that we are allowed to manipulate. And most memory locations are invalid pointers. I said a typical computer has a few billion memory locations, and a program has a handful of objects. So if I have 2 valid memory locations and I have billions of invalid locations, the vast majority of locations are invalid. Here's how we declare a pointer in C++. If capital T is a data type, like int or something, then T star is the data type of a pointer to an object of type T. So continuing the int example, int is a data type name, so int star is the data type of a pointer to an int, or the location of an int. Pointers are uninitialized by default. That's consistent with them being considered kind of an integer type. In C++, the integer types, int, unsigned, and others, are uninitialized by default. So when you declare an int or unsigned or a pointer, it's your responsibility as the programmer to write code that initializes that variable. Therefore, in this code here, int star p, that declares a pointer called p that could hold the location of an int, but p is uninitialized, and so most likely p is invalid at this point in the code, because when you have an uninitialized variable, it holds an unpredictable value, you might say a random value, and there's a very slim chance that that happens to be a valid pointer. So how do we get valid pointers? We get them with the address of operator, which is written with an ampersand. So if x is an object and capital T is the type of x, then ampersand x is an expression that gives you the location of x, or a pointer to x. The data type of this expression is T star, the location of x's data type. So for example, if I declare int score equals 5, that creates an int object holding the number 5. And int star ptr, that declares a pointer to an int. At this spot in the code on the left-hand side of the equal sign, ptr is still uninitialized, but then I initialize it with ampersand score. We pronounce that the address of score. So find the location of score in memory. Whatever memory location that is, that's what ampersand score produces. And so at this moment, ptr is pointing at score. And here's how I would sketch this. Let me say a little bit more about how we sketch pointers. In order to sketch a pointer, we draw an arrow. So here I've got my arrow. So it's a straight line with an arrowhead at the end to indicate which way the pointer goes. A curve would be okay too, but the important thing is that it's clear where this starts and where it ends, in which direction it's going. The pointer starts where the pointer is, where the pointer itself is located. So PTR is the beginning of my pointer, and the arrow ends at the location that the pointer points to, so score. Once we have a pointer, we want to use it for something, and one way to use it is to dereference the pointer. That basically means follow the pointer and get what it points to. So if P is a pointer, then star P is an expression that yields an L value for the object at P's location. L value, again, is some C++ jargon that means a value that can be on the left-hand side or the right-hand side of an assignment, meaning you can read the value or you can write the value. So basically that means follow the pointer. Now remember that a pointer can be valid or invalid, and if P is a valid pointer, this works great, no problem, but if P is an invalid pointer, you get undefined behavior. What that means in the standard technically is that the program could do anything. It's undefined, it could crash, it could erase values in memory, it could allow a virus to get installed, I don't know, anything, it could break something physically. But in practice, what that almost always means, undefined behavior, is the program crashes, probably with a segmentation fault error. So if P is an invalid pointer and you try to dereference it, what happens is that's some illegal location, and the operating system usually intervenes and says, hey, you're not allowed to access that memory location, and it shuts down your program to prevent it from causing any further damage. Here's an example of dereferencing. I create an int x equals 6. Here's a sketch of that situation. After creating int star pointer is address of x. So pointer is pointing at x, x is holding the value 6. The next line of code here, y, is dereference pointer. This is dereferencing in action, and this would assign y the value of 6 because it says, okay, take the PTR pointer, star means follow it. So if I start at PTR and follow that arrow, I get to 6. That's because PTR is pointing at x and x is holding 6 right now. So follow the arrow, you get a int that's 6, and so y is assigned 6. And so after that statement executes, y holds 6. This is showing the dereference expression in an R value position, meaning on the right-hand side, reading. You can also put the dereference operation on the left-hand side of a assignment. That's the L value option, and that has the effect of changing whatever pointer points to. So this says follow pointer. We find a location of an int and write into that int the number 100. So that has the effect of changing x to hold 100. X is now overwritten. It doesn't hold 6 anymore. Now x holds 100 because what we did is set this up where pointer points at x, pointer is the location of x, and then this last line of code says go to the location of pointer, change that value to 100. That permanently changes x to 100, so the 6 is gone. Now y is still 6. We didn't do anything to disrupt that. Y still holds 6, but x implicitly gets changed from 6 to 100 right here. And that's one reason why pointers can be a little bit counterintuitive, because this statement here doesn't explicitly say anything about x, but it changes x despite that. A pointer can be reassigned. That means kind of moving the pointer, just assigning a new location to it. That's fine. We're going to review references soon. References cannot be reassigned. That's one reason we're mentioning this. So if you reassign a pointer, that means that the pointer now points at a different location than it used to. So here's an example of reassigning PTR. The first part of this code is similar to the previous slide. I create my int x that holds 6. I create my int y that's holding 5 now. Pointer is initialized the address of x. I would sketch that as an arrow PTR to x. Now I reassign pointer to the address of y. So now what's going to happen is PTR changes, and now PTR holds the location of y. I would say pointer points at y. So we're not pointing at x anymore. It doesn't change 6 or 5. The values of x and y are unchanged, but PTR is pointing at a different object. Okay, I want to categorize the way that pointers can get invalid. I mentioned before that an invalid pointer is a pointer that does not actually point to a valid object, and a lot of different memory locations have invalid pointers. There's a few ways that these can arise. One is an uninitialized pointer. So if I declare, say, a string star p1, that's legal code. It compiles and runs, but p1 at this moment is probably invalid because it's uninitialized. Another way that we can get an invalid pointer is a null pointer. A null pointer is address number 0, and there's a very strong convention in programming that address 0 means invalid. There's nothing there. In C++, there's a keyword called nullptr, null pointer, for that. So here I'm explicitly saying p2 points at null, nothing, and that's not a valid pointer. I can't dereference p2. Another way that a pointer can become invalid is what's called a dangling pointer. That happens when you delete an object or free dynamic memory. When you free dynamic memory, you're not allowed to access that memory anymore. You gave it away. So you're not allowed to access it. That's an invalid pointer. So here's an example. Pointer to a character, char star p3 is new char. That's legal. I allocated a new character. Then I delete p3. That's legal as well. I'm freeing the memory, the one character that p3 is pointing to. But p3 is now a dangling pointer. I still have the variable p3 in scope, but if I dereference p3, that's undefined behavior because that character object has been freed. Dereferencing an invalid pointer is a logic error. There's three major categories of error: a compile error, a runtime error, and a logic error. So dereferencing an invalid pointer is considered a logic error. That means it's a programmer's mistake when writing the code. That once a pointer is invalid, it's our job to make sure we do not write code that dereferences that. That means that after these statements execute, I am not allowed to dereference P1. So star P1, that is off limits. I shouldn't have code that does star P1. The same goes for star P2 and star P3.